excitement that we're about to reach here. I'm going to do this Unit 2 progress check free response question number 2. I'm going to do it in front of you as an example for the kind of things you often see in AP Classroom. And I guess what I mean mostly by that is both its structure and the fact that there are no numbers. There's just equations and variables. So let's just dig right in. We have a sled of mass m sliding down a rough ramp with a constant speed of v initial. The angle between the ramp and the horizontal is theta, as shown above. The ramp smoothly transitions to a horizontal surface. The coefficients of static and kinetic friction between the sled and the ramp are mu s and mu k, respectively. The ramp and the horizontal surface are made of identical materials. The dot in figure 2 represents the sled when it's sliding down the ramp at a constant speed. That is critical information, because now we know there's no acceleration. Draw and label arrows that represent the force, but not the components, that are exerted on the sled. Each force in your free body diagram must be represented by a distinct arrow starting on and pointing away from the dot. Okay, well, it is a sled sliding down a ramp, and what I do know, of course, is that there is a force of gravity straight toward the center of the Earth, and I'm going to label it as such. I know that there's a contact force between the sled and the ramp. There's a contact force, and it's perpendicular to the surface, force normal. And I know there's a friction force up the ramp, because if there weren't, it would be accelerating. So the friction force is here. And I labeled the forces. Okay? Now, I want you to notice something. Very important. It said draw and label the forces, but it also says not components in the parentheses right here. And so not components means don't do this. I'm going to do this because I want to show you, but gravity has an x-axis component, and gravity has a y-axis component, but it said do not include those. So I'm going to get rid of them. Okay, or nearly get rid of them. Okay, so just got some points. There's the good news. I've already earned some points, and I know that every one of you could do what I just did so far. Okay, now, starting with Newton's second law, derive an expression for the force of friction exerted on the sled. I'm not even going to read that second part. That might scare me right now, so I'm going to move that out of view. Starting with Newton's second equation, derive an expression for the force of friction on the sled. Okay, this is something that I actually take a little bit of umbrage with, and the reason is because force of friction is equal and opposite to something else we need to know about, which is the amount of gravity on the x-axis. I'm going to pretend I'm turning this into an AP reader, but I would still somewhere, maybe on scrap paper, I would probably pull out, why don't I pull out a piece of scrap paper here? On a piece of scrap paper, I might redraw this. And because I need that gravitational component to solve this problem. All right, so I've got gravity straight down, as we said. I've got normal straight up, as we said. And I've got friction. Those are the three main forces. I think the reason they say not to draw components is because they want to make sure you are not confusing components with other forces. There are three forces on this block. However, one of them has some componentry, right? So gravity is pulling on the x-axis that hard. And since this thing is in constant motion, we know that the force of gravity on the x-axis is equal and opposite to friction. Now, very quickly, you know this too. If this angle is theta, we've been through this a bunch of times, then this is theta. And if that's theta, this is theta, which means we're looking for the opposite leg, and we know the hypotenuse is force of gravity. So gravity on the x-axis is force gravity sine theta. Okay? That's important. So I'm going to go back to here, and I'm going to go to my Newton's law statement, keeping in mind this business right here, even though I'm not allowed to show it here. So that's a little bit of, that's a little weird, but we're just going to roll with it. Newton's second law, okay, well, Newton's second law, that should come pretty quickly. The sum of the forces equals m times a. And we're quick to point out that a is what? Acceleration is 0. So the sum of the forces equals 0 newtons. Okay, well, let's sum those forces. Let's sum those forces because we're talking about x-axis, right? We're talking about the x-axis. We're trying to solve for force friction. Let me double check that. Is that what it says? Derive an expression for the force of friction exerted on the sled. Yes, we want friction, and it is equal and opposite to FGR sine theta. So let's see. I'm going to say, I'm just going to call this the positive x-axis. So I'm going to say that the force of gravity on the x-axis minus the force of friction equals 0 newtons. I'm going to add force of friction to the other side, and I'm going to get force of friction is equal to force gravity on the x-axis. And now we're sort of there, except I'm not allowed to write FGR sub x. I'm allowed to express my answer in terms of m, mu, theta, and physical constants such as g. Okay, well, so we have some points here, but we haven't achieved all the points yet. I'm just going to do this and keep writing. Let's see. Force of friction is force of gravity on the x-axis. Well, that's mg sine theta. Expression for the force of friction exerted on the sled, and well, there it is. The force of friction is mg sine theta. Now, express your answer in terms of m, mu k, and theta. Okay, well, how about this? Force of friction is mu force normal. Mu force normal is mg sine theta. That's literally the definition of friction. The force of friction is mu times force normal. You've seen this plenty of times. Mu is force of friction over force normal. So friction is mu force normal, and mu force normal is mg sine theta. I'm not allowed to have force normal in there, but I am allowed to have m and g. So how about this? Mu mg cos theta equals mg sine theta. Okay, so I guess I'm really running with this because I'm already sort of, actually our answer to our answer to B1, an expression for the force of friction, our answer to B1 would be really right here. Okay, what is force friction? It's mg sine theta. Am I allowed to have mg sine theta? I'm allowed to have m, I'm allowed to have g, and I'm allowed to have sine theta. Okay, 2 though, I'm already headed for the answer to B2, which is derive an expression for the coefficient of kinetic friction between the object and the ramp. Okay, so it comes right from the same F equals ma statement. Express your answer in terms of the same business. Okay, so I'm after mu, and when I substituted mu force normal in for friction, I got mu force normal is mu mg cos theta. Wait a minute, where'd that mg cos theta come from? The contact force is equal and opposite to the amount of gravity on the y-axis. So that brown arrow I just drew, that's mg on the y-axis. That's force of gravity on the y-axis. Contact force is equal and opposite to it. And so what is mg on the y-axis equal to? Well, it's mg cos theta, right? Because the adjacent leg is what we're after. And the adjacent leg is mg on the y-axis, which is going to be equal and opposite to force normal. And we have the hypotenuse as the force of gravity, which is just mg. Right, so let's see, adjacent hypotenuse. The cosine of an angle is adjacent over hypotenuse. The cosine of this angle is adjacent, mg on the y-axis over mg. And so what is mg on the y-axis? Multiply both sides by mg. Mg on the y-axis is mg cos theta. This brown arrow here is mg cos theta. And so force normal is mg cos theta, positive. That's where that came from. Mu force normal is mu mg cos theta. And that's equal to the pull down the ramp by gravity. That's mg sine theta. Now we're after mu, so I'm just going to go ahead and solve this for mu by dividing by mg cos theta. So mu is mg sine theta over mg cos theta. And you could leave it just like that, and they would give you full credit because here, derive an expression for the coefficient of kinetic friction, mu, in terms of m, mu, theta, and physical constants. There's nothing here that's not allowed. Okay? However, we could simplify it, right? Because I got mg over mg, that cancels, and sine theta over cos theta is tan theta. So really, if you really want to impress them, you would just say mu is tan theta. But I think what they're looking for is a step back from that to here. Okay, that was the hard part. We had to write Newton's law, and then we had to substitute it in. Now, in just a moment, I bet you they're going to ask us to do something with this. Let's find out. From time t equals 0 to t equals 1, the sled slides down the ramp at a constant speed. At t equals t1, the sled reaches the bottom of the ramp, and from t1 to 2t1, the sled continues to slide on the horizontal surface. All right, so from t to t0, it's going down the ramp. From t0 to t1, it's going down the ramp, and from t1 to t2, it's coming to a stop. Okay, so let's see here. On the axis shown in the figure before, sketch a graph of the speed of the sled as a function of time from t equals 0 to t equals twice t1, which is when it comes to a stop. So first of all, I know it's going to be going 0 when it gets here. And I know that it reached the bottom of the ramp at t1, and I know something really important about the velocity. The velocity, it was clearly stated, is constant on the ramp because gravity's pulling down and friction's pulling back, and so it's just going down the ramp at some speed. Now, I guess the question is here, how do I connect this point to this point? Is it kind of like this? Is it like this? Or is it like this? It's one of those three. It's got to be. Which one is it? I don't know. Well, let's go figure it out. We are looking for the relationship. This is accelerated motion, right? It's going at some velocity and then it stops. So we have a change in velocity here, and that change in velocity is taking place as a function of time. So we need to know how velocity and time are interrelated during acceleration, and we go to the kinematic equations and we pull a few out and we say v is v initial plus at. There's our answer right there. If we had displacement distance instead of time on this axis, we'd be saying something like v squared is v initial squared plus twice a change in x. And there's a big difference here, right? If it's velocity and time, we have v being linearly proportional to t. There's no exponential stuff happening whatsoever, right? Velocity is going to vary linearly with time. So that's our answer. It's that line right there, okay? If this was distance down here instead of time, then we'd be tackling something else. How does velocity vary with displacement? Well, then we'd be then we'd be choosing a different curve, but a different shape. But we're not. So we're good to go here. Indicate how the shape of the graph between 0 and 1 would change, if at all, if the angle of the ramp were increased. Okay. Well, if the angle of that ramp were increased, then we wouldn't have the situation that we have right now where friction is equal and opposite to gravity. If the angle of that ramp were increased, friction's going to stay the same, but gravity on the x-axis will increase, right? So if it looked more like this, and gravity was like this, friction is still short. Friction is still mu force normal, right? But force normal is diminishing. Okay, force normal is diminishing, so actually friction gets smaller, and friction goes down. That's actually a shorter arrow. It should be a shorter arrow, and furthermore, gravity has grown. So if the ramp gets steeper, the gravity on the x-axis increases, and the friction decreases. This is no longer constant motion. This is going to accelerate down the ramp now. There's more force down than up. It is no longer in equilibrium, right? And so what happens here is it's going to speed up on the way down. So the only thing that would happen here, I'm just going to draw it in a different color. It wants me to explain it, and I will, but let me just say this. What would happen would be that it would start at some velocity, and it would speed up while it was on the ramp. The velocity would increase, and then it would go down. And if it still stops in twice t1, then it's going to go to that same point, and it's still going to be a straight line. But the big difference is that would no longer be constant motion because the forces are no longer balanced. And that's what I'm going to write here. How would it change? Let's see, the shape of the graph. So the line between t equals 0 and t equals 1, or t1, t equals 0, t0 and t1, would have a positive slope. Would have a positive slope, indicating an increasing velocity. The velocity would no longer be constant. The velocity would no longer be constant. The velocity would be increasing on a steeper ramp. The velocity would be increasing on a steeper ramp because force gravity on the x-axis would increase, and force friction would decrease due to a smaller normal force. The forces would no longer be in balance. The forces would no longer be in equilibrium. Spelled it wrong. Equilibrium. The forces would no longer be in equilibrium. Gravity on the x-axis would be a larger value than force friction. Okay, so I just got full marks on this problem here. There's a lot to do, but I love these because they're really driven by that first sketch, right? They have you do a first sketch with free body diagrams, and then what they have you do is come up with a statement which then generally gets substituted into something later, right? We kind of ran with it right through both parts here. But that's generally how these things go. And then they ask you to derive something in terms of very specific values. So you've got to do substitutions and get what's not allowed out of there. And then they generally ask you some sort of a qualitative question, like, hey, what would the graph look like? What would happen if this happened or the other thing happened? And to explain yourself, to explain your logic with respect to the given event. The one that you see tomorrow, I'm going to tell you right now, is going to be regarding circular motion, a ball on a string kind of thing. And it's going to be a little bit of an easier lift than this one. But I think this is fair game. We just have to get used to the approach. It's different than the physics LE stuff. It's different than university physics from textbooks, but I really like them. They're very different than what I was trained on, but they're really thought-provoking questions, and they really go after the big ideas. So there's just a little exposure to a sample dynamics open response problem. I hope you are as thrilled with it as I am, and I also hope that you're still awake. And if not, wake up. Time to go. All righty. Have a good day, people. See you soon.